Hi, I'm Brecka, and I'm an undergraduate student at the University of Wisconsin-Stevens Point. Today, I will be talking about using light-level geolocators to determine nest attentiveness of wood ducks breeding in central Wisconsin. Wood ducks are cavity nesters, utilizing trees or other natural structures or man-made nest boxes to lay their eggs. They are considered income breeders as they need to acquire all their resources during their breeding period, as opposed to capital breeders like many goose species that go into a breeding season with enough reserves to focus solely on their incubation. Because of this, wood ducks must take daily nest breaks throughout their incubation period, and this results in a trade-off between maintaining body condition and caring for their developing eggs. Geolocators record time-stamped light-level data at frequent and regular intervals. They are a cost-effective and minimally invasive way for wildlife managers to track individual locations based on estimated daily twilight times and build a better understanding of geography and timing of migratory movements. However, there has been recent application for analyzing breeding behaviors, especially in cavity nesters like wood ducks. Here is an example of a light graph of a female wood duck that was caught in a decoy trap. This kind of graph can get kind of tricky to read, so I'll try to orient you. The black parts of the graph indicate no light reaching the geolocator, while the lighter parts are where light was recorded. The x-axis is time in months, and the y-axis is the hour of the day. The red dashed line in the middle of the graph is midnight, and the green lines represent sunrise and sunset. Each vertical sliver represents a single day that was recorded. The first block of black on the left side of the screen is when the geolocator was in a bag before deployment. This bird was caught while she was laying eggs. Outlined in yellow, you can see short periods of darkness in the morning. This is when she was laying her eggs, and I'll show what that looks like at a finer scale in a later slide. Outlined in blue is incubation. Here you can see a period of about 30 days where she spent a lot of time in the nest cavity. You may also notice blocks of light during this period, especially in the morning and the evening. This is when she took her nest breaks, which I will focus on for the rest of this presentation. With the data we've gained, our objective is to better understand the breeding habits of wood ducks in central Wisconsin and investigate relationships between their behaviors and environmental factors. We hypothesize that as average temperatures increase, hens will take longer nest breaks, and when individuals are structurally larger, they will also take longer nest breaks. The female birds that were used for this study were caught and banded in central Wisconsin during the spring and summer of 2020 and 2021 as part of a larger research project looking at migration patterns. To catch these birds, decoy or baited swim-in traps were used in addition to catching birds in known nest boxes. Once in hand, they were fitted with geolocator bands, and several morphometric measurements like age, sex, weight, diagonal tarsus, and wing chord were recorded. After releasing these birds, the bands were recovered via hunter recovery or recaptured during our banding efforts. These bands are archival, meaning we need them back in order to download the data into the Interproc software. From there, I manually examined each day of deployment, looking for breeding behaviors, and I recorded them in Excel. We then used a generalized linear mixed model for data analysis. Raw data from geolocators can show the daily activity of female wood ducks. I will go over just a few of the breeding events in this presentation, but if you are interested in learning more, I do have a poster presentation with in-depth methods of how we categorized each breeding event. For these graphs, time is on the x-axis and light level is on the y-axis. Below the red line is the threshold for complete darkness. Here we see a normal day for a bird. light levels steadily increase from sunrise to midday and then slowly decrease until sunset. Here's an example of an egg-laying event. You can see that the bird went into the nest cavity, spent about an hour laying her egg, then left for the rest of the day. These events usually occur in the morning and continue for about 8 to 12 days before incubation begins. Once she has laid all her eggs, she will begin incubation. This is a dramatic difference compared to the background graph. She will spend about 10 to 12 hours of the day in the nest cavity tending to her eggs, but you may notice two significant spikes in light levels in the morning and evening. These are nest breaks where she leaves the cavity to feed. We recorded the timing, duration, and frequency of these breaks and tried to determine any relationships with environmental or morphometric factors. We used geolocator data from 11 females to run a generalized linear mixed model for data analysis. Because we have samples for each day a band was deployed, we added a random effect of individuals to control for pseudo-replication in our regression. We examined how temperature and diagonal tarsus may affect the time spent off the nest and found some interesting results, which I will show in my effect plots. We also ran tests on Julian date, but found no significant relationship, and our sample size was not sufficient to run tests on age. For the first relationship, we looked at average temperature and the average number of nest break minutes or time spent off the nest. Average temperature data was collected from the National Oceanic and Atmospheric Administration website and was recorded for each day a bird was incubating. We saw a positive relationship between temperature and nest break minutes. When average temperature increased, birds tended to spend more time off the nest. For example, when temperatures were close to freezing, birds spent only 140 minutes off the nest. Compare that to temperatures closer to 80 degrees. Birds spent about 100 more minutes off the nest at those temperatures. Here we looked at diagonal tarsus and time spent off the nest. We used diagonal tarsus as an index of structure size because it is a fixed variable. Birds were weighed at capture, but we only got one measurement, so it would not be useful for showing changes over time. Again, we see a positive relationship between the length of the tarsus, indicating a structurally larger bird, and the time spent off the nest for that individual. Birds with a tarsus of 32 millimeters spent an average of 150 minutes off the nest, while those with a measurement of 36 millimeters averaged 210 minutes off the nest. While recording data, I noticed that evening breaks were consistently longer than morning breaks, so we ran a regression to see if there was a significant difference. Evening breaks averaged about 100 minutes, while the morning breaks often averaged only 75 minutes. Overall, we saw several different relationships between environmental and morphometric factors and the amount of time spent off the nest. As temperatures increased, nest breaks also increased. This could be due to the fact that hens do not feel the need to sit on their nests when it's warmer out because there is less risk of their eggs getting cold. Additionally, warmer temperatures usually occur later in incubation when a female may be struggling to maintain her body condition. She may feel the need to take longer breaks in search of food. We saw nest breaks increase in structurally larger females. These birds could need more nutrients to sustain their body condition and spend more time feeding. Evening breaks were generally longer than morning breaks. Connecting ideas from temperature, this makes sense. There are generally cooler temperatures in the morning, and a bird may not be willing to be off her eggs for a long amount of time. With these preliminary results, there are several management implications and practical uses for this information. Flushing birds during important breeding events could have an impact on the success of those nests. Studies examining incubation interruption showed measurable effects on behavior of flushed birds. So if our goal is to reduce disturbance of breeding birds, we can use the timing of nest breaks to approach known nests to do things like count or candle eggs. Conversely, if we want to catch females sitting on nests, we know approximately when she will return from her morning nest break and when she will leave for her evening nest break, allowing us to predict a window of time where we can catch that bird. At the most basic level, these results can show us how crucial quality wetlands are for the success of these birds. Providing food opportunities for wood ducks while they are incubating is likely a deciding factor of the risks they are willing to take to reproduce. If a hen has good nutritional resources throughout the breeding period, she can, theoretically, start incubation earlier, spend more time on the nest, hatch her eggs quicker, and get those ducklings on the ground to increase their chance of survival. Overall, it is evident that there are major trade-offs between body condition and reproduction, and a combination of factors likely contribute to the decisions a hen decides to make to increase her fitness. However, in order to fully understand what affects the nest breaks of wood ducks, more research is needed, and thankfully, more and more geolocators are being returned. With that, I'd like to thank Ben Sedinger and Andrew Greenawalt for the help with this project and the several entities that made this research possible. Please feel free to contact me if you have any other questions. Thank you.